In this video, we'll discuss the definitions related to probability distributions, and specifically, probability distributions for variables that are discrete. A random variable is a variable that is a single numerical outcome from a probability experiment. It must be a number. Going back to the definitions we learned on the first day of class, if the number is discrete, then we say it's a discrete random variable. If the number is continuous, we say it's a continuous random variable. We will cover continuous random variables in the next chapter. Recall that a number is discrete when the numbers are listable or countable. So essentially, this includes integers and money. A probability distribution gives every possible value of the random variable and the probabilities for all the values. Because we've listed everything that can happen, when we add up the probabilities, they must add up to 1. If it's less than 1, then we didn't list all the possible values. If it's more than 1, then we've made a mistake in assigning probabilities. Probability distributions can be expressed as a table, a graph, or a formula. For discrete random variables, because the values are listable, we will very often list them in a table. Here's an example. If we're rolling a fair 6-sided die, the number we get could be 1, 2, 3, 4, 5, or 6. And every number has a probability of 1/6 of coming up on a die, so this is a discrete probability distribution. What about my other favorite probability experiment, flipping coins? I know y'all get tired of these examples, but they're so easy to imagine. So here's our sample space again, but these are not random variables because they're not numbers. A random variable must be a number. So how do I turn flipping 3 coins into a random variable? I'm going to let X be the number of heads that I get when I flip that coin 3 times. This could also work for counting the number of tails. I just have to decide what I need to count. So I'm going to let X be the number of heads, and my probability distribution looks like this. I might get 0 heads, or 1, or 2, or 3. I can find the probabilities by looking at the sample space. For example, to find the probability of 1 head, I look at the sample space and see that there are 3 ways to get 1 head out of 8 events in the sample space, so the probability is 3/8. I can figure out the other values the same way, and I can graph these probabilities too, or in this case, take a graph from the Math is Fun website. And when we graph, we put the X values on the X-axis, and we graph the probabilities on the vertical axis. To find the mean and standard deviation for a probability distribution, we use the following formulas. We can't simply take a mean of the numbers. It needs to be a weighted mean that takes into account that some values have higher probabilities than others. Next, I'll show you how these formulas work. Unfortunately, there aren't any built-in calculator functions for these formulas. We will practice these in class. Let's compute the mean and standard deviation for this probability distribution. But before we do that, let's look more closely at this distribution. Is this really a discrete probability distribution? First of all, it doesn't give us any probabilities. It says these are relative frequencies. But that's allowed because we can use the relative frequency as an approximation to the probability. I don't know anything about what X measures. This is just an example I found in the book. So do I know if they listed all the values for X? It appears that they did because all the probabilities add to 1. So let's look at the formula again. To find the mean of the probability distribution, we take every X and its probability and we multiply them. Then we take the sum of all those values and that's the mean. So let's go back to the example. You'll see the X values multiplied by the probabilities in the 3rd column. At the bottom of the 3rd column, you see the sum of the products is 32. That's our mean. That's it. We don't do anything else. If you use this formula for the case when all the probabilities are equal, you will get the same mean as if you added everything and divided by the number of values. If you want to test this out, try it with the random variable we get from rolling one fair die. For the formula for the standard deviation, I'll use the first form. It is equivalent to the second form, and some people prefer that version, but I'm going to use the first version. The formula says that we'll subtract the mean from every x value, square the difference, multiply that by the probability, and then we add those together. That's our variance, and then we take the square root. So let's go back to the example. I've listed the x values and the probabilities in the first two columns. First, we subtract the mean of 32, which we found a couple of slides ago, from every value. Those are the values you see in column 3. In column 4, I square the differences from column 3, and in column 5, I multiplied those squared differences in column 4 by the probabilities. Then we add the values in column 5 to get a sum of 171. That's our variance for the probability distribution. To get the standard deviation, we take the square root of 171 to get 13.1. Probability theory got its start in the casinos of Europe, so a lot of the theory has to do with gambling. The mathematicians of the time came up with this idea of expected value. It turns out that the expected value, the expected winnings, are exactly the same as the mean. So another name for the mean is the expected value. So here's a dice game I invented to play with a loaded die. I'll pause here a little bit and let you read about the game. We want to find the expected value of our profits, so we need to put a dollar amount to the outcomes. I've listed all the possible values from the die, along with their probabilities. If you roll anything less than 6, you win $5. If you roll a 6, you lose $5, so your profit is negative $5. Remember that this is a loaded die, and the probability of getting a 6 is 1/2. The probabilities for the other numbers are 1/10, so we fill those in the table. Then I multiply all the x values, the dollar amounts, by the probabilities. And when I add those, I get a sum of 0. So the expected value is $0. Another way to do this problem, especially when we're talking about expected value, is to think about the options of winning versus losing. If you win, you get $5. If you lose, your profit is negative $5. You lose if you roll a 6. And the probability of a 6 is 1/2, so the probability of losing is 1/2. Therefore, the probability of winning is also 1/2. We multiply the values by the probability to get $2.50 and negative $2.50, and we add those together, and again, we get an expected value of $0. And this brings me to another definition. A game is statistically fair when the expected value is 0. In review, a random variable is a variable that is a single numerical outcome from a probability experiment, and it must be a number. A probability distribution gives every possible value of the random variable and the probabilities for all the values, and we know it's correct when we add up all the probabilities and they add to 1.